Thanks so much, Janina. I'm really excited to see Janina again after it's been, I think, probably a little bit more than 4 years since I've seen you. So speaking of 4 years ago, the last time I was here at iOS Conf SG in January of 2020, which I showed this graphic of how cold it was in Madison, Wisconsin, which is where I lived at the time. And I talked about how glad I was to be out of Wisconsin in the dead of winter. And Karma clearly heard that, laughed really, really hard, and then said, okay, COVID is going to trap you in Wisconsin for 15 straight months. And during which time you are going to get so stir-crazy that you and your partner go hiking on, not at, on a lake on a day where the high temperature is a balmy negative 23 degrees Celsius. So this time I will confine my comments to saying, I am delighted to be here. Time seems really straightforward when you first start working with it. And since this is a 35-minute talk, you will probably not be surprised to learn that it absolutely is not. But when you start, you think, okay, I have the current date, and I want to add an hour. So you say, since you know a date is a representation of time in seconds, you think, okay, to add an hour, I'll just say that I need to add 60 seconds times 60 minutes. And to add a day, just multiply that by the 24 hours in a day, and then for a year, multiply that by the 365 days in a year. And so you go ahead and you set up some code to grab the date, turn your calculated number into a time interval, add it together, and then print it out. And if you do this anytime in the month of January or February of 2024, when you run it, you will get the correct answer for now, but you'll be off by a date for a year from now. And that is because 2024 is a leap year, here to throw all of your simple calculations straight into the trash. And you start to think, this may be harder than it appears. And it turns out that if you try to think of every single thing that needs to be taken into account when figuring out how to represent a time stored in a computer in a way that makes sense to humans, you wind up sounding like you're slowly losing your mind, and there is a fairly decent chance you will actually be losing your mind as well. So I want to start with what a computer thinks a date is. And in Swift in particular, that's, again, represented as a good old date. Now, Apple defines a date as a specific point in time, independent of any calendar or time zone. And this is all well and good, but this clearly has got some spoilers about other things we're going to talk about later. So if you want a spoiler-free version of this, you're going to have to go with my definition of date, which is that it is a fixed point in time. And some of the methods on it give you some idea of how that fixed time is represented under the hood, because when you see something like time interval since 1970, you think, aha, this is when computer languages were really starting to come into more common use. Maybe everybody just agreed that this was the beginning of time at that point. But then the Foundation developers found out they also had to start accounting for all the programmers who were born well after 1970, and they came up with the more loosely named reference date. I assume because they didn't want anyone to think about what year it actually was under the hood, which is probably good because while the place where the time interval since 1970 starts is midnight UTC on the first day of January 1970, the reference date could have been anything. Instead, they selected the 1st of January 2001 at midnight UTC because apparently somebody thought putting it right on the border of the year 2000 would be far too easy. And of course, because of this discrepancy, Apple provides a convenient static method for figuring out the diff between the two commonly used reference dates. I will save you opening a playground to find out. It is a difference of 978,307,200 seconds. Fun facts for bar trivia at the world's dorkiest bar. And that count of seconds is basically the way the computers think about dates, as a monotonically increasing number of seconds since a fixed point in time. But as I just said, that is absolutely not the way humans think about time. There are a lot of pieces of the puzzle to figure out how to take these fairly basic structures of a count of seconds since a given time and translate them into something people actually understand. And a good place to start with this is the calendar. So Apple says that a calendar is a definition of the relationships between calendar units and absolute points in time, providing features for calculation and comparison of dates. But what I say that a calendar is the only way to relate an absolute time point in time to anything that humans are actually going to be able to understand. And this is where the messiness of humanity starts to really rear its ugly head, especially in the form of days that just flat out don't exist in the middle of calendars. because for many of us used to dealing with international communication, we think of the calendar in terms of 12 months, most either 30 or 31 days, but then there's this one weird one that's usually 28 and sometimes 29. But when we're talking about that calendar, we're primarily discussing the Gregorian calendar. And let me nerd out more than a little bit here because I am fascinated by how various things we take for granted came to be. So it's called Gregorian because in October of 1582, Pope Gregory XIII finalized the reforms that led to the system that is used fairly internationally now. The main calendar in use before that in the Christian world was the Julian calendar, which, yes, was indeed proposed by everyone's favorite Roman, Julius Caesar. And it turns out he is the jerk that you can blame for leap years, because his calendar calculated that the Earth rotated around the sun every 365 and a quarter days. So to correct for that unevenness, you just kind of crowbarred an extra day in every 4 years to make things even out. Easy peasy, right? The Romans were not quite as good at astronomy as they thought they were, because it turns out that in reality, the Earth actually orbits the sun just a tiny bit less frequently than they thought. This isn't terribly perceptible over the course of a few years, but the difference meant that the calendar would drift by about 3 days every 400 years. There have been a few attempts over the years to adjust for this. By the time of the Gregorian changeover, however, the Julian calendar was off by almost 10 days from where the equinoxes, or points where the day and night are the same length, were actually taking place. So good old Greg over here approved some changes to the calendar that bears his name, including removing 10 days so that the calendar went straight from October 4th, 1582 to October 15th, 1582. And there wasn't anything particularly special about those dates. In fact, it's so arbitrary that if you look in the open source version of Foundation, you will see that the Gregorian calendar is actually hard-coded to begin on October 15th, 1582. And most countries have since adopted the Gregorian calendar for civil use, although some of them with their own local twists that will absolutely kill any math you think you're doing. For instance, in the Japanese calendar, everything is identical to the Gregorian calendar except the year. The year is instead calculated by what year of the emperor's reign it is. And this leads to all kinds of fun problems when an emperor dies, or in the case of Emperor Akihito in 2019, abdicates. So the day he abdicated was at April 30th, Heisei 31. And his son, Naruhito, took the throne and the next day, and he was May 1st, Reiwa 1. So for Heisei 31, anything after April 30th doesn't exist. And for Reiwa 1, anything before May 1st doesn't exist. Whole swaths of months of dates, and they're just gone. And that is before you even start dealing with lunisolar calendars, which are calculated by how frequently the moon orbits around the Earth rather than by how frequently the Earth orbits around the sun. But then, in order to line back up with solar calendars like the Gregorian calendar, they have to add an extra month in every few years. Trying to keep track of all of this is absolutely maddening. So one of the earliest things you learn when dealing with dates is that you absolutely should not try to manage all of this yourself. Apple has done a whole ton of work to get all of this as right as they possibly can. And at least if they've messed it up, you can blame it on them. So what are the conveniences that Apple provides for doing this? Well, to get a specific calendar, you can just pass its identifier to an initializer. That's pretty straightforward if you actually know what calendar you want to use for something. But most of the time, your user will have a particular calendar that they usually work with, which may or may not be the same one as you usually work with. So how do you know how your user wants to see things? The easiest answer is to grab the auto-updating current calendar from the system, because that will give you a lot of information about what sort of calendar the user wants to see things displayed in. Okay, great. Now that you know how to get their preferred calendar, what do you do to actually display a date? So this is where we run into our friend the date formatter. And the Apple definition of this is that instances of date formatter create string representations of date objects and convert textual representation of date and time into date objects. Whereas my definition is that a date formatter is the thing you should use to turn a date into a user-facing string. And this is where the puzzle pieces really start to come together, because the way you tell a date formatter what calendar it should use to display things is by just handing it the calendar directly, then telling that formatter to generate a string based on that calendar. And lo and behold, you get absolutely nothing. And that's because the formatter knows what calendar you want something displayed in, but it has no idea what information you actually want. And you could hand it a raw date format, which will print out exactly what you tell it to no matter where someone is located. I found this is mostly useful for moving back and forth between dates and strings, especially from APIs where you know what the format is going to be, but you also know it's not something standardized like ISO 8601. So if you plan to do this, I highly, highly recommend Ben Sherman from NS Screencast's public service site, nsdateformatter.com. I cannot tell you how frequently I reference this when I need to remember how to write a date format and not have it accidentally use minutes instead of months. However, while having a very specific format is sometimes what you want, something you're going to want far more often is to use one of the Apple-provided date styles, because in addition to providing sensible defaults, you also can adjust the output based on locale. So if I just grab the auto-updating current calendar like I did here and tell it to use the full date style, it realizes I'm in Singapore and outputs the date in a format that makes sense for Singapore. However, I can also pretend I'm back in the United States by setting a specific locale on the formatter, and it will then print the date I handed in Merca format without me having to do anything else. The other thing you can do is if you definitely know you want to print something in a particular calendar, you can set up a formatter which is instantiated specifically with that calendar. In this case, we're going to use the Islamic calendar. And again, if you give it a date style, it'll print something that makes sense for your current location, but you can again hand it a different location so that it prints in exactly the format you want it to. Now, in addition to the primary date formatter, there are several other really useful date formatters that you may want to look into for the specific use cases they handle, so you don't have to. A date interval formatter is really useful for displaying how long a period is between two dates. Date components formatter is basically what it says in the tin. It takes a set of date components and formats them. This is really, really useful for APIs which return a set of date components rather than an actual date. The ISO 8601 date formatter is very useful for going back and forth from dates to strings that match the ISO 8601 date format, which if your backend team prefers to not be in constant pain, is probably the best way to send strings for an API. And finally, there's the relative date formatter, which for some reason is only available in Swift, and it'll take a date to compare, then a relative date, and format it like 1 hour ago, or yesterday, or tomorrow. If you're writing a social media client, you will get very familiar with that very quickly. Oh, also, so I promised in my talk abstract that I'd tell you how the Foundation team managed to speed up date formatters 1.5 times, and this is how you know I wrote the abstract well before I actually wrote the talk, because I looked into it, and the answer is basically exactly what you'd think. They created Swift versions of almost everything and stopped wasting computing power bridging back and forth between Swift and Objective-C. Sorry, it's a little bit obvious. So anyway, now that we've talked about how to turn a date into a user-facing string and a string into a date, let's talk about turning that date into its component parts. And you'll be shocked to hear the way you do this in Swift is through the date component structure. And Apple's definition is that date components are a date or time specified in terms of units such as year, month, day, hour, and minute to be evaluated in a calendar system and time zone. And while we've talked about calendars, we haven't talked about time zones yet. So the spoiler-free version of this is that date components are the way you define which parts of a date you actually care about. And one way to see what I mean by that is to look at the initializer for date components, which tells you not only what the various parts of a date are that could be part of a date components object, but also provides a really excellent excuse to show you another meme. No, actually what it does is it tells you that in any date components object, these things could be there or not. And when you're working with a calendar, there are two ways you can work with the date components. You can get a set of components out of a date, or you can get a date from a set of components. So we're going to start with getting components out of a given date and time. So the example I'm going to use here is the time this talk was scheduled to begin, Friday, January 19th, 2024 at 2:10 p.m. Singapore time. And if all I want to know is what the hour and minute are, then I can just ask for them by passing those components in as part of the set that I want back. Then when I query that set of components for the hour and minute, I'll get those back as optionals with a value since I explicitly asked for them. However, if I ask the date components object for a component that wasn't one of the ones that I passed as part of this list, such as the second component, when I try to print that, it will wind up returning nil. So remember, you won't get a component unless you specifically ask for it using this API. Okay, so that's getting components out of a date. Now let's talk about turning a set of components into a date. So if I want to take the year of 2024, the first month and the 19th day, and then turn them into a date using the Gregorian calendar, then use a formatter that I set up with the Gregorian calendar, I'll get everything coming out the way I want it to, because all of my operations are taking place within the same calendar. Now, one thing that's interesting is to add a format for the time style. And you'll see that because you didn't pass in any time components, the time registers as midnight. Or if you're going in 24-hour time instead of AM, PM, 0 hours, 0 minutes. In fact, if you just take away all the components except for the year, you'll wind up with January 1st, 2024 at midnight, because those are the first valid values of each of the nil components that were passed into the calendar. And you can, of course, pass in more components to do things like get the exact time that this talk was scheduled for. So let's back up for a second and forget about time and go back to working with just dates for a minute. Now, if you take these date components and say, okay, I'm going to try to use the Islamic calendar to make a date from these components, but then I'm going to use a Gregorian formatter to print back out so I can see if the components that I passed in created the same date. And what you'll get is that the date you've created off the Islamic calendar is now several hundred years in the future, in an entirely different month and an entirely different day number. So why is that? Well, it's easier to see when you take that same result and print it out with a formatter you've handed the Islamic calendar, which will tell you that it's the 19th day of Muharram, 2024 years after the Prophet Muhammad migrated to Medina. And the fact that the day and the year match what those components are here should tip you off to what's happened here. You gave it components that were designed to be used by a Gregorian calendar, but you handed them to an Islamic calendar. And that Islamic calendar has different baselines for everything. So the absolute point in time it creates, based on those components, is going to be different. Now, in theory, a way to deal with this is to pass a calendar into your date components object. And according to the documentation, that will tell the receiving calendar what the original calendar was for the components being passed in. In the real world, this does absolutely nothing. You can confirm this by looking at the logic of date from components in the open source version of Foundation. The calendar component is completely ignored. I have absolutely no idea why. So to properly change a date from one calendar to another, you really have to use the calendar in which you've created your components to create a date object that represents a specific point in time, then hand that specific point in time over to something with the other calendar to translate into something users of that other calendar can understand. So I want to discuss one more weirdness that people have imposed on dates and time. We'll start by heading back to this slide. And you probably noticed something there a couple of times, the abbreviation UTC, which stands for Coordinated Universal Time. However, because the abbreviations don't match up, and that makes me twitch very hard, I tend to think of it more as universal time, coordinated. It's a way of representing that time overall is just constantly increasing, never decreasing or changing, or dealing with human representations of time. And the fact that no matter where you are on this big, weird planet of ours, spinning out in space and having different parts light and dark at the same time, you can represent time in the exact same way is very convenient for working with computers. So why do we need this coordinated universal time? Because humans have invented something called the time zone. And this is where our concepts of space and time start to come together. Because as Apple says, a time zone is information about standard time conventions associated with a specific geopolitical region. The way that I put it is that a time zone is the way humans reconcile the rotation of the Earth and a need to coordinate time across physical and political boundaries. And again, I'm going to get a little bit into the weeds here, but you can basically blame railroads and the telegraph for the existence of time zones. So before time zones were invented, noon was determined by whenever the sun was at its highest point. And at the speed a horse and carriage could go, you really couldn't travel all that far all that quickly. So being in every area, looking up and going, yeah, that's about the middle, was working out fine. Then when you introduce railroads into the equation, something that used to be a journey of at least a day, such as the journey from Boston to New York, became a matter of hours. And the roughly 12-minute difference between solar noon at one and solar noon at the other meant that if you set your watch in Boston, you would be early for your train that left at noon in New York because you thought it was 12 minutes later than the New Yorkers thought it was. But if you set your watch in New York, your watch showed it being 12 minutes earlier than the Bostonians thought it was. So if that train left at noon Boston time, you would probably miss it. So the idea of having one area where the time was always the same regardless of the exact position of the sun was born from railroads. So people could more reliably figure out when a train was going to show up. And in Britain, since the country isn't that large, they invented something called Greenwich Mean Time, which basically said, right, we're telling the whole country they're setting their clocks to noon whenever it's actually noon in Greenwich, and they're all gonna like it or lump it. And then the telegraph was invented to allow nearly instant communication over very long distances, across entire continents and eventually even oceans. And so there became a need to coordinate time across much larger swaths of the world. And while you can see the time zones here have taken a lot of zigs and zags across what are generally political boundaries over the years, if you trim this down to just the very bottom, you can see where this idea started. For every 15 degrees of change in longitude, a new time zone would occur. Why would it be an hour later for 15 degrees? Because if you divide the number of degrees of longitude that exists by the number of hours in the day, that's what you get. So you offset an hour for each time zone from GMT, and then when you get back around the Earth, the hour gets wrapped around to the next day. Over the years, this has gotten considerably more complicated than just looking at what longitudes were. In fact, I can tell you that this particular map is at least 13 years old because it shows that Samoa and American Samoa are in different time zones, when that is no longer the case. In fact, here, they're on opposite sides of the international date line, which is the point where we go from being later in the day behind a UTC to earlier in the day ahead of UTC. So American Samoa was initially on the behind side of the international date line because of their history as an American colony. The United States is on the behind side as well. But in 2011, they decided that because they do way more trade with Samoa and Australia than with the United States, because those two places are far closer physically than the US, they wanted to switch which side of the international date line they were on to be closer to their trading partners temporally. So they just went ahead and skipped a day. In this story, the BBC wrote that as the clock struck midnight on 29 December ended, Samoa fast-forwarded to 31 December, missing out on 30 December entirely, which means the fact that this BBC story about it is dated 30 December 2011, the exact day which did not exist on American Samoa, is very, very funny to me. So again, this is a situation where you should absolutely not attempt to manage all of this yourself manually. Apple is hooked into the official list of all time zone changes that come from the international organizations that coordinate all of this. And they have a really easy way to get all of the time zones that the system currently knows about. And it can get very, very granular if it needs to. The American state of Indiana has 8 different named identifiers for time zones to account for hyperlocal differences in the handling of daylight savings time, or as people in Indiana call it, fast time and slow time. The South American country of Argentina tops even that with 12 different named time zones. And again, you don't want to manage this yourself. Luckily, in addition to the auto-updating current calendar, you can grab the auto-updating current time zone to find out exactly what time you need to display everything in if what you're trying to do is display things in the user's time. And this is part, again, of why UTC is so useful. Because if you're storing, for example, the takeoff and landing times of a flight from New York to Singapore, which takes off at 10 p.m. one evening in New York and then lands at 5 a.m. 2 days later in Singapore, even though only 18 and a half hours have actually elapsed. It can be really hard to figure out how to display that in a calendar. But if everything is stored in UTC, it's easy to figure out exactly what time things need to be in that calendar by applying an offset of their time zone from UTC. Oh wait, did I say UTC? Because if you actually instantiate a time zone with the UTC identifier and then turn around and say, okay, give me the identifier, that's a nasty little secret out of the bag. UTC is actually GMT under the hood. Remember Greenwich Mean Time, that thing the British invented to get trains to show up at the agreed upon times? It is back. And the technical reason you will hear about all this is that GMT is an actual time zone that is used in certain countries for various parts of the year. And UTC is a standard, which is based on Greenwich Mean Time. So any calendrical calculations you need to do will actually be based on the deviation from GMT, since you can't calculate a deviation in time zones from a thing that isn't technically a time zone. I kind of hate this explanation because it is way, way farther into the weeds than you should have to get in order to understand what you need to do in order to make these calculations. So this leads me nicely into a couple of general pieces of advice that I found to be helpful in dealing with dates and times. The simplest one is to only bother working with the components that you actually need. So when I was working on auto-generating calendars for Zinnia, the journaling app that I work for, I essentially made a separate struct that just held on to the year, month, and day for a date, because they were the only things you actually needed in order to make a calendar display the dates in a month. It doesn't matter what time or time zone you're dealing with, the month, day, and year don't change for this use case. So those components were all I wound up using. Now, particularly after a talk like this one, where you learn exactly how complicated this all can be, it's unbelievably easy to overthink this and do way more work than you actually need to if you're not careful. Step back, look at what exactly matters for a particular use case, and only deal with the parts that you actually care about. That being said, when you start dealing with the more complex aspects of dates, especially when time and time zones start getting involved, it also turns out it's incredibly easy to underestimate. And whenever something is easy to both overestimate and underestimate how difficult it is, the best way to find out if you've correctly estimated is to test the hell out of everything that you're doing programmatically against what you, as a human living in your calendar and your time zone, know about what to expect about when things happen. And obviously, you can't test every single time that ever happens. That would result in infinitely long tests. But there are a few places where you can get a lot of feedback on whether you're handling things properly. The first is when you create a date in one time zone and read it in another. This is a great way to make sure that you're storing and pulling things out properly, although one piece of advice I have for writing these tests is to watch out for what time your continuous integration machine or container thinks it is. If your tests are passing locally and failing on CI, you're probably creating dates in a way that is specific to the local time zone of the machine the tests are running on. Instead, use a calendar that you set up manually in your test to ensure that you always know what calendar and what time zone things are being created in. So the next place to add tests that get you bang for your buck is when one of the date components suddenly becomes lower than it had been. For example, when the end of a day rolls over, suddenly the hours go 23 to 0, and then when the month rolls over, it goes anywhere between 28 and 31 in the Gregorian calendar, back down to 1, and when the year rolls over, suddenly the number of months rolls back from 12 or 13, depending on the calendar, back to 1. Especially when you're doing date math, these are really, really helpful things to test to make sure that you're getting the answers that you're expecting. Another place to test is when you get things that only happen once in a great while, but at defined times. Things like the rollover from February 28th to February 29th to March 1st in leap years for the Gregorian calendar, or whatever years in lunisolar calendars wind up having that extra month to bring them back into line with solar calendars. And then there is the most infamous case, of course, daylight savings time. That point where we arbitrarily jump forward or fall back by an hour because someone in the early 1900s thought it would help farmers save electricity or something. In fact, this leads me to a fun example of the subtleties that testing can uncover because I screwed this up just last week. And only because I added tests around the daylight savings rollover did I realize anything was wrong. So to start with, I was working with two different methods around moving a date around. Getting a date from a set of components, and then getting a date by adding a set of components to a date. So what I wanted to do was get an arbitrary number of the next n hours so I could use them to display an hourly schedule, not dissimilar from this one that you'd see in the macOS calendar app. So in my first stab at doing this, I was using the API that gets a date from a set of components and adjusting the components by adding whatever number of hours I needed to the components. And by default, if you create a set of date components indicating you are at March 9th at 25 hours, what you'll actually get back is March 10th at 1 hour. Seems legit, right? So my later work wound up using the other method, which is the date by adding components method. In this method, you're still doing a loop, but in this loop, you take the original date, you add a set of date components representing the span of time you want to change it by, and then use that for the updated date. So I had a couple of test cases for this. The first was starting at the current date, then adjusting the components by or adding 12 hours to the given date. And the second one was checking what we call in the United States spring forward when daylight savings time begins. At 2 a.m. Eastern time on March 10th of this year, the date displayed to users will suddenly move ahead an hour and be 3 a.m. So when I ran the tests for the current date, I got basically what I expected, which was that in both cases, the output was exactly the same. So these tests passed immediately. And then they passed for every rollover I tried, right up until I hit testing the daylight savings rollover. When you look at the results, you'll see that when you add the components representing a span of time, you go midnight, then you get that jump to 3 a.m., then 4 a.m. And this is what you would expect, so this test passed. However, when you're adjusting the components, you get this very weird set of results that says, okay, it's 1 a.m., and then it's got that expected jump to 3 a.m., but then it's 3 a.m. again, and then it's 4 a.m., and that is not right. And I was very confused by this result. I was like, okay, what am I missing here? And so I reached out to Dave DeLong, who, by dint of volunteering to fix a bug with NS Date Picker about 13 years ago, wound up knowing way more about how dates and time work than pretty much anybody in the iOS ecosystem. He also runs the invaluable resource yourcalendaricalfallacyis.com, where you can learn exactly how many assumptions you have wrong about dates. I assure you it's going to be a lot of them. Now, my incorrect assumption was clearly that these two APIs did essentially the same thing. And after talking to Dave, I realized that's absolutely not true. Because when you're using the adjustment method and calling date from date components, what you're actually telling the calendar to do is find the closest matching date to the components you've handed it. And when you apply that to a daylight savings change where you're moving forward an hour in the US, you start with telling it you're looking for March 9 at 25 hours. It says, okay, given the way that hours wrap around to days, what you're actually looking for is March 10th at 1 a.m. and says, okay, here you go. Here's March 10th at 1 a.m. But then when you tell it you're looking for March 9th at 26 hours, it says, okay, so the way the hours wrap, that should be March 10th at 2 a.m. Now, because this is the exact hour of the daylight savings transition, that hour doesn't actually exist. So Dave from Components tries to find the next closest thing that does exist, which in this case is March 10th at 3 a.m. So that's all well and good until you say in the next go around of the loop that you want March 9th at 27 hours. And the way that wraps around, it goes to March 10th at 3 a.m. And it says, okay, that does exist. Here you go, March 10th at 3 a.m. And it's giving you exactly what you asked for according to this API. But when you compare it to what a user would expect to see, instead of seeing a jump from 1 a.m. straight to 3 a.m., they see 1 a.m., then two different instances of 3 a.m. That's absolutely not right, and that is where my test failed. So why does this work when you instead add date components to a different date? So this is because this API is literally saying, what is the amount of time later than the past date that you want to see? So when you hand it March 9th at 5 p.m. and ask for 8 hours later, you get March 10th at 1 a.m. And when you hand it March 9th at 5 p.m. and ask for 9 hours later, you get March 10th at 3 a.m. It's no longer searching for anything or trying to match anything. It's literally just adding that amount of time to the original date. And so then when you ask for March 9th at 5 p.m. plus 10 hours, it gives you the expected March 10th at 4 a.m. And so it was reassuring to get a right answer and finally be able to understand why I got a right answer. But the fact that you can have an answer that's right about 99% of the time and still royally screw up daylight savings transition is basically why I drink. Finally, we have come to the obligatory summary slide. So in this talk, you have learned that computers think about dates in a linear and specific fashion, while humans think about dates in a whole lot of different weird ways, influenced by history and politics and Julius Caesar and the popes of the 1500s and the moon and the sun and railroads and telegraphs. And because this all gets monstrously complex, you should take advantage of the Foundation APIs, whether within UIKit and AppKit or in the new open source version of Foundation, to try to handle as much of what you want to try to do as possible. This also includes letting Apple figure out what date and time styles would make the most sense to display to a user, given their locale, time zone, and calendar preferences. And finally, no matter how well you think you know these things, you will find something subtle that you messed up when you test transitions, especially for daylight savings time. So test the ever-loving crap out of them. One last thing, this is a very personal note. I want to dedicate this talk about time to a guy who doesn't really have a lot of it left. That's my cousin Mark. He has spent the last year fighting a type of brain cancer called glioblastoma. Unfortunately, it's a fight that a vanishingly small number of people win nowadays. There's some really promising research going on that could help a ton in the future. So if you liked this talk, do me a favor and throw a couple of bucks at a foundation in your area that deals with glioblastoma. Help them pay for research that could mean in the future nobody has to go through the incredibly rough time that Mark has gone through. So I've included links here to the National University of Singapore Cancer Institute, for those of you who are local, as well as to the American Glioblastoma Foundation. Google your country name and glioblastoma for more resources in your local area. Thank you all very much for listening, and I hope you all enjoy the rest of the conference.
Thanks, Ellen. That was an incredible talk, and of course, we're all very sorry about your cousin. Are you up for Q&A, Ellen, or are you running off stage already? You're pulling an Adrian on us. Yeah, we have a little bit of time for Q&A. If anybody has.
I can answer questions. I just can't guarantee you that the answers are going to be right.
Let's see. Do we have any questions? Okay, there's one up there. Also, please put your questions in Discord, so I don't have to run.
Hello.
Hi.
Thank you for a talk about the time. My question is about maybe it's a time to get rid of this complexity. For instance, we can get rid of the time zones. For instance, when we used to work remotely for a couple of years from a different time zones, and when my colleague says like, let's meet at 2, I'm working. I know I'm working in GMT +8. Yeah. But I don't know if he's in Poland or in Canarian. Which time zone is that? Yeah. Yeah, we have a Google Meet. We have that, but I think this time we don't need these time zones. What do you think? Well, and I think this is a thing that when you're working, my whole company is completely remote as well. So one of the things that we do is we have a time zone that we agree whenever somebody posts a date, unless they specify otherwise, that time and date are going to be in Pacific Standard Time or Pacific, whatever the current daylight savings part of Pacific time it is. And it's something where, you could post it always in UTC, but people have a much harder time making that adjustment from the time system that they use all day, all the time, to a time system that's more designed for computers to work with than it is for humans. And so I agree that it's definitely something where, like, if you have a team that is spread out over a large period of time, you have to spend the time to make sure that when you say, hey, let's meet at 2 p.m., you say 2 p.m., Central European time, or you say 2 p.m. Eastern time, or whatever time zone that you're actually talking about, so the other person can figure out what the hell time it's going to be at their time. In terms of just chucking it and just going with UTC for everything, I think that's hard because I think it's a little bit of sunk cost fallacy, but people really have a good idea of what time means. When should it be light? When should it be dark? And if you're in a place like Singapore that's a 12-hour offset from GMT, you're going to wind up having noon be in the middle of the night and midnight be in the middle of the day. And there's just, it's one of those things where this is why we have sort of a separate system of like, here's the thing that computers can understand because it is just a single point in time. And then everything else that we have to do to translate that into something that humans can understand, we're essentially dealing with legacy code to say, okay, this is what almost everybody can actually understand about how dates and time work. So let's change that through to something that actually makes sense to the vast majority of people. So that's my take.
Thanks, Ellen. I think we can probably agree that we don't need daylight savings, at least.
I think the only time I ever agreed with Marco Rubio on anything was when he introduced a resolution in the United States Senate to get rid of daylight, or actually, it was more make daylight savings time permanent. So it was just move everything an hour ahead of where it has been and call it a day, never change it again.
Sounds great. Yeah. One more question on Discord.
Yes.
What is the difference between calendar.current and calendar.auto-updating current?
Ooh, that's a good one. So calendar.current is basically a way of saying, I want a reference to exactly what the calendar is at this time that I am accessing it. If you ask for auto-updating current, it says, okay, I'm going to get the calendar not just at the time that I'm accessing it, but anytime I access it in the future, I will get the updated calendar. So like, let's say I get on a plane, I go from New York to Singapore, and a single app that's been running in the background the whole time comes back up. If it had said, okay, I want calendar.current, then it would still think I was in New York. But if it was calendar.auto-updating current, then it would know I'm in Singapore. Does that make sense?
Yeah. Thank you, Ellen. I think that's all the time we have for questions today.